The second solution for unconstrained optimization is the Newton's method and conjugate gradient. The assumption is that the objective function f(x) is twice differentiable and the second order is not equal to 0. Let's proceed step by step. First, compute the Taylor expansion of the function at a given point x0. And we can calculate the f(x) in this formula. Then we take the first derivative of this function to be equal to 0, which is the direction needed to reach the minima of the approximation. Hence, we can get the result for each iteration. This formula can be generalized with the following updating rule and repeat. Let's see it geometrically. As we can see, as approaching the x star, the distance between the two x values approach toward 0. It is noted that it might be possible that xm and x star never perfectly match. So the idea of the Newton method is to find the minimum of the target objective. We have to start from the random starting point with a second-order Taylor extension to approximate our curve. Then, compute the minimum of the extension, which means take its first derivative and set it equal to 0. The minimum of the quadratic approximation will be the new value of x. Then, the iterative process keeps repeating, and the resulting series of xn tends to converge towards the minimum of the target. As we can see the characteristic of the Newton's methods, these two graphs show the update process. Both iterate 3 times. The number of decimal places of accuracy is approximately doubled in each iteration. Global convergence is poor if the starting point is far from the minima. In most cases, Newton's method combined with the globalization strategy can effectively reduce the step size until the function decreases. At last, we can get the basic idea of the conjugate direction method. It can be regarded as being between the gradient methods in the first order and Newton's method in the second order. The goal of the conjugate direction method is to accelerate the convergence rate of gradient descent while avoiding the high computational cost of Newton's. By using this method, an n-dimensional quadratic form can be minimized in at most n conjugate descent steps. From the two-dimensional control point, there are 3 different starting points. However, the minimum is reached in exactly 2 steps. That's the end of our mathematics basics. This course mainly introduced the essential mathematics topics used in AI, including linear algebra, probability and statistics, as well as the optimization problems. It is the foundation for further AI learning. For more information, you could visit the Huawei eLearning website and Huawei Support Case Library. Thank you for your listening.